Good morning or good afternoon, everyone. I'm Haoran Yu, a PhD student from Rice University and the supervision of Professor Ian Lin. Today, I'm very excited to present our work, Early-Bird GCN's graph network optimization towards more efficient GCN training and inference via joint early-bird tickets. The general background of this project is that graph convolutional networks, or GCNs, show better performance on graph-based data than convolutional neural networks. In general, GCNs includes two phases, aggregation and combination. As shown in the figure below, the first aggregation phase aims to aggregate the information of neighbors. The second combination phase will further combine the aggregated neighbors' information and node itself information. Although GCNs achieve good performance on graph-based data, recent breakthroughs on SOTA GCNs rely on massive graph data and computational power, making GCN training and inference very challenging. For example, as compared to the CNN, GCN have prohibitive training or inference costs. A mere two-layer GCN model with 32 hidden units can cost 19 GFLOPS to process the Reddit graph, while a medium-scale CNN model less than 50 only require 8 GFLOPS to inference on ImageNet. So it costs 2 times more flops and even 5,000 times latency than Resident 50 when accelerated using the CPU. Then naturally, the question in our mind is why training and inference GCNs cost so much? We attribute, we attribute this to three reasons. First, real-world graphs are very large and irregular and often have complex neighbor connections. For example, there are 232,000 nodes in Reddit graph, and each node have about 50 neighbors, so it's quite a complex local neighborhood. Second, the dimension of node features can be very high. Each node in the citation graph can have over 3,000 features. Third, the graph adjacent matrices has extremely high sparsity and often exceed 99.9% as compared to the 10 to 50% in the sparse CNN models. So that will lead to slower training or inference. As such, efficient GCN training and inference has become a very important research problem. For efficient GCN training or inference, the common practice includes three steps. We first pre-train a dense network, as denoted by the red circle here. Then, the second step is to sparsify the graphs based on the pre-trained GCN networks. After extracting the subgraph, we will retrain the GCN network on it. As this pipeline shows, its training cost can be prohibitively high because it requires to train the GCNs on full graphs, and also require train, prune, and retrain three steps. Such training process is tedious. While there are opportunities to alleviate such training or inference costs based on previous research work, Early-Bird tree, which claims the subnetworks can be drawn at early training stages and can also achieve comparable accuracy as the original dense network, which we termed as Early-Bird tickets, so that we can identify the subnetworks with only 10 to 20% training epochs. We further hypothesize that such early bird phenomena also exist for GCNs, and more aggressively, both subgraphs and subnetworks could be drawn at early training stages, which we term as joint early bird tickets. And as shown in the bottom figure, we only need to train 10 to 20% training process for extracting such subgraphs and subnetworks. To achieve this goal, there are two research questions. First, does early bird ticket existence also hold for the graphs in the GCNs? Second, it is still unclear how to jointly optimize the graphs and GCN networks, which corresponds to feature aggregation and combination phases respectively. To answer those questions, in particular, we make three contributions in this project. First, we discover the existence of graph early-bird tickets and propose a low-cost detector to automatically detect them. Second, we propose a graph network co-optimization framework to detect the joint early-bird ticket from both graphs and GCN networks. Third, We leverage the existence of graph early-bird tickets and the proposed co-optimization framework to develop an efficient GCN training scheme, which we dubbed as GEBT, graph early-bird training. Next, I will elaborate on each point. The first contribution is that we empirically find that the graph early-bird ticket exists. As shown in the above figure, we visualize the retraining accuracy of the joint subgraphs at different training stages, where the x-axis represents the epoch where we draw the subgraphs, and the y-axis represents the retraining accuracy. Each line or each color in this graph represents different subgraph sparsity, and the dashed black line represents the accuracy on unpruned graphs. We find that the retraining accuracy of the subgraph drawn at early training stages can be comparable or even better than the fully trained unpruned graphs. We call such subgraphs as graph early-bird tickets. Next, we extend the experiments to different GCN graphs and consistently find that such graph early-bird tickets can exist across various GCN graphs. As compared to the previous SOTA, graph early-bird tickets only require 10 to 20% training and potentially can lead to much less training cost while achieve comparable or even better retraining accuracy. And for this point, we will validate this in the experiment part. However, there is still one problem. Although we can find that early-bird ticket exists, we do not know when to stop the training or specification to identify it. So to solve this problem, next, we propose a low-cost detector to automatically detect the emergence of graph early-bird tickets. In particular, we use a boundary mask to represent the joint subnetworks, and we compute the Hamming distance of such masks in consecutive epochs, and then draw the early-bird tickets once the distance is smaller than the specific threshold, and in practice, the threshold is preset at 0.1. And as shown in the right bottom corner, we visualize the Hamming distance during the training process. In this figure, both x and y-axis represents the epoch where the mask is drawn from, and each point denotes the Hamming distance between x epoch and y epoch. And such distances are normalized to be within 0 and 1, where 0 means the connectivity of joint subnetworks or subgraphs have been converged and is shown as warm color, and 1 means the connectivity of joint subgraphs have not been converged and is shown as a cooler color. We find that the graph early-bird ticket at 10 epoch for Cora and 15 epoch for the Cetacea graphs. And also, the detection overhead is very low. It can be less than 0.1% of the total training cost. Then we further design experiments to validate that the proposed detector generally works under different graphs and pruning ratio scenarios. As shown in this figure, the x-axis represents the training epochs, while y-axis represents the normalized graph distance, and different lines represent different subgraph sparsities. We can see that the graph early-bird ticket can be identified during the early training stages, 10 to 20 epochs, and across different sparsity ratios and different graph data sets. Till now, we have validated and identified the graph early-bird tickets. Then the research question is that, can we make it more efficient? Our second contribution aims to identify both subgraphs and subnetworks. The motivation is to offer more efficient GCN training and inference, and the method is to iteratively update both the GCN graphs and the networks. For updating GCN networks, we consider the cross-entropy loss following the previous GCN work. And in this formula, the Z represents the prediction and Y are true labels. So this represents cross-entropy loss for updating the GCN networks W. Well, for updating the GCN graphs, we instead will update the adjacent matrices of the graph, and we consider both the cross-entropy loss and the sparse regularization term to update it. For the regularization term, it will be 0 if the sparsity meets the target ratio, and it will be infinite if the sparsity doesn't meet the target ratio. In above figure, it visualizes the comparison between the co-optimization framework and the previous SOTA SGCNs, and the x-axis represents the inference flops, while y-axis represents the retraining accuracy. Different lines represent different methods. The purple line represents the SOTA SGCN work, and other colors or other lines represents the proposed co-optimization framework and the different sparsity ratios. We find that the proposed co-optimization achieve better accuracy and efficiency trade-offs than the previous SOTA work. Also, just finding subgraphs and subnetworks are not enough. We still want to find them from early training stages. To achieve this goal, we test the training accuracy of subnetworks or subgraphs drawn from different epochs during the training process. As shown in this figure, the x-axis represents the epoch where subgraphs and subnetworks are drawn from, and the y-axis represents the retraining accuracies. Different line represents the subgraph ratios, and the different subplot represents the subnetwork sparsity ratios. We find that both subgraphs and subnetworks could be drawn at earlier stages that can achieve comparable or even better accuracy than that of dense GCN graphs and networks, which we term as joint early-bird tickets. Next, we will design a low-cost detector to automatically detect the joint early-bird tickets. Well, the approach is very similar to the graph early-bird tickets detection. The only difference here is that we consider masks to represent both subgraphs and subnetworks, and will join joint early-bird tickets according to the sum of Hamming distance of the subnetwork mask and Hamming distance of subgraph masks. Once the Hamming distance is smaller than the given threshold, we will stop training and draw the joint early-bird tickets. And also, the detection overhead is less than 0.1% of the total training cost. We further design experiments to validate that the proposed detector works under different graphs or different pruning ratio scenarios. As shown in this figure, the x-axis represents the training epoch, while y-axis represents the normalized sum distance. And the different lines represent different sparsity ratio pairs for the subgraph and subnetworks. We find that the proposed detector can consistently draw the joint early-bird ticket at early training stages, and the joint early-bird tickets actually emerge at 10 to 30 epochs. That is quite early. And our third contribution is to leverage the graph early-bird tickets and also the proposed co-optimization framework to develop an efficient training and inference scheme via drawing the joint early-bird tickets. And in summary, our proposed GEBT here, graph early-bird train, can help to reduce 80% to 86% training costs and 85 to 88% inference costs. Next, we evaluate the graph early-bird tickets across 5 GCN models, 7 graph datasets using both the efficiency metric and accuracy metric. For the efficiency metric, we consider training flops and inference flops. For the accuracy metric, we consider node classification accuracy or F1 scores are hit at 50. And we compare GBT against the 10 baselines, including both the efficient GCN training baseline, SGCN, and also other SOTA GCN algorithm baselines. In this frame, we evaluate the GBT over SOTA GCN training baselines. And in this figure, the x-axis represents both the inference flops in the first line and the training flops in the second line. And the y-axis is the retraining accuracy, while different lines represent different methods. As we can see that the GBT via drawing graph early-bird tickets achieve 25 to 32% training flops reduction while offering comparable accuracies. And GBT via joint early-bird tickets more aggressively achieve 80 to 86% and 85 to 88% reduction in training flops and inference flops respectively, meanwhile offering comparable accuracy. And then we compare the proposed GPT over SOTA GCN algorithms. In this table, we evaluate the GPT as compared to SOTA GCN algorithms on three citation graphs. GPT achieved 2.6 times to 10 times inference flops reduction while offering a comparable accuracy range. And also, we extend the comparison to larger datasets, PPI and Reddit. And in this comparison, the GPT improvement is consistent. GPT helps to reduce up to 84 inference flops and up to 83.5% training flops, and the comparable or even higher F1 scores. Next, we evaluate GPT on deep GCNs and larger graphs. So the improvement is consistent. GPT reduced 4.2 times and 7.5 times inference flops and up to 10 times training flops reductions, and the comparable or even higher accuracy range. And we also visualize the training curve in the above figure, while the x-axis represents the training flops, and the y-axis is the testing accuracy. We can see that the proposed GPT indeed can make the training faster and more efficient. So to summarize, we for the first time discover the existence of graph Early-Bird tickets and detect the low-cost detector to automatically detect them. And then we propose a graph network co-optimization framework to automatically detect the joint Early-Bird tickets from both graph and GCN networks. Third, we develop an efficient GCN training schemes via the via the graph Early-Bird tickets and the joint Early-Bird tickets, which we dubbed as GBT. Thank you for your time and listening.